Hello again. So last time I introduced this lecture series by talking about the two fundamental problems in calculus, the derivative and the integral. And I stated that both of these problems can be solved with the idea of a limit. So a limit is essentially where I look at the behavior of a function around a certain point instead of actually at the point itself. Okay, I'm looking at what the function is doing as I'm approaching some x equals c. And I stated that there are certain conditions where the limit would not exist. So I want to quickly review those. So these three situations where a limit does not exist. So a jump or an infinite discontinuity. Recall that a jump discontinuity is essentially where the limit approaches different values from both sides of x equals c, right? They approach different values because there's a whole range of y values that the function essentially skips. So it's discontinuous at x equals c, and it goes up a range of y values before it continues. An infinite discontinuity is essentially a vertical asymptote where on both sides of x equals c, you're approaching some sort of form of infinity, either positive or negative infinity, like in the case of tangent of x as x approaches pi over 2. Okay, the second situation is an infinite oscillation. And I'm not talking about a regular oscillation like a trig function such as sine of x, because you know that periodically repeats every 2 pi units. I'm talking about a situation where as you get closer and closer to some value of x equals c, like in the case of x equals 2 with this function, okay, you switch between two y values more and more quickly, right? Okay, so it's really hard to tell exactly what happens because you keep switching more fast as you're approaching that c value. And finally, the one-sided limits I mentioned before, it's not too big of a deal. You have to be able to approach x equals c from both sides for the limit to exist. Okay, so I want to spend some time talking about infinite discontinuities. So recall what an infinite discontinuity is. So an infinite discontinuity exists when there's a vertical asymptote. If there is some value, some vertical line x equals c, such that the function approaches positive and negative infinity from either side of that. Okay, so what that looks like in terms of limits would be something like, well, if the limit as x approaches c of f of x is being divided by something that you can't substitute. I can't just plug in x equals c right here and have that equal anything meaningful, because I'd be dividing by 0. Okay, and this is different from a point discontinuity, because if you recall what a point discontinuity states, point discontinuity looks like this. It's x approaches c of some f of x times x minus c over x minus c. So by adding in x minus c divided by x minus c, I'm removing a point from my function. This function is the same exact thing as if I were to cancel these, but when I cancel these, I'm adding that point back in. And by adding that point back in, I'm allowing myself to plug in c to make this limit equal to f of c. Okay, but what is the limit as x approaches c of this guy equal if there's a vertical asymptote? Well, to give you an example, I'd like to point out the graph of secant of x, a fun trig function. Okay, so secant of x has asymptotes at negative pi over 2 and pi over 2. Actually, every pi units aside from that, so there would be another one at 3 pi over 2. So what you would have are these vertical asymptotes. Okay, and the graph looks something like this. So if I asked you what the limit as x approached pi over 2 is, you wouldn't be able to tell me. Because at pi over 2, they're approaching different things if I'm on the left or the right. The one-sided limits are different, and therefore I told you that the limit doesn't exist. Well, that's technically not true if you consult a lot of textbooks. What they're going to say is the following. If you are approaching some value that happens to be a vertical asymptote, this limit is actually going to be equal to plus or minus infinity. Right? And essentially what that means is this guy could be positive infinity or negative infinity, depending on the one-sided limits. So in the case of secant of x, if I'm approaching from the left side, I'm going off to positive infinity. If I'm approaching from the right-hand side, I'm approaching negative infinity. Now, I technically have a problem with this because a limit cannot equal a concept. Infinity is just a concept, it is not a number, ergo I have a problem with this. But a lot of textbooks and teachers say screw with that, so it equals positive or negative infinity depending on what it approaches. Okay, so it's going to go off without bound to some flavor of infinity. You just have to find out what that is depending on whether you're approaching from the left or the right. So this idea of the vertical asymptote is called an infinite limit. All right, so that's great. At a given point, x equals c, my function goes off without bound to positive or negative infinity. Now what if I wanted to know what happens in the long run, if x approached infinity itself? Well, that's actually called a limit at infinity. And what I'm going to say about that, well, it's the following. So I'm going to start out with an example. So there's a principle in thermodynamics called Newton's law of cooling, and it states the following. Given some sort of a thermodynamic interaction where heat's being exchanged between an object and its surroundings, eventually there will be a point in time when they don't interact anymore, where their temperature will not change. So if it's wintertime and I take a hot cup of coffee and put it outside, yeah, that cup of coffee is going to get colder, but it's not going to go to freezing. It's not going to be exactly the environment temperature, right? It's not going to be -20 eventually because it's water. It's not going to change as quickly as you might think. So in this case, if I were to graph what happens over time, so let's say that I have a situation where I'm graphing heat on the y-axis over time, I might start off at some sort of a temperature, and I'm going to keep going. I'm going to decrease, obviously, if I'm that coffee cup. I'm going to decrease, and eventually I'm going to level out. I'm going to level out, and what I'm essentially going to get is a value that it equals. We'll call that value A. So this is known as a limit at infinity. What I'm going to say about that is these limits at infinity are essentially when the limit as x approaches infinity or negative infinity, some flavor of infinity of a function, when that equals a distinguished value. In that case, you have what's called a horizontal asymptote. I'm going to tell you how to deal with that in just a second. So in the case of Newton's law of cooling, in this case, there's a horizontal asymptote, and therefore a limit at infinity at the value y equals A. Right, and this seems like a very, very simple concept, but if you take a look at it, it's actually pretty interesting, right? So like a cold-blooded animal such as a snake, its temperature, its internal temperature changes with the surrounding environment, but it doesn't change. It essentially levels off, right? So if it's -20 degrees outside, that snake's not instantly going to die because its internal temperature is going to change to be -20. Its temperature is going to change and decrease, but it's going to level off. So all cold-blooded animals essentially have this leveling off point, and it's because of this law of cooling. All right, so in order to tackle these problems where we have limits at infinity, I want to bring the following to your attention. So a definition that I'd like you to know is that the limit as x approaches infinity of 1 divided by x is essentially 0. And there are ways of proving this, but I'm not gonna do that in this video. And I mean, there are ways of verifying this. You can graph the function on your graphing calculator and see that yeah, it has a horizontal asymptote and it just keeps going and going. Or if I increase this guy, 1 over 10, 1 over 100, 1 over a million, that approaches values that are so small that you can essentially consider them 0. And finally, if I flip this guy and I take the limit as x approaches infinity of x, as x grows, my function value increases as well. Okay, so if x goes to infinity, the function goes to infinity. So if I flip this, the opposite is true. As my x increases, my function decreases to a value of 0. All right? So I want us to suppose the following. Suppose I have a function that looks like this. I have some sort of a coefficient c multiplying an x to some power a. Okay, and then I have another x value on a different power, and these powers are all decreasing. And I'm dividing this by some sort of an x to the b, okay, where there's a coefficient in front of this guy, and then all these other terms are descending in terms of their powers. Well, what I can say, is I can factor this x to the a out of this expression entirely. Okay, so a and b are just numbers, they don't really matter what they are, but if I factor that out, I get the following. Well, this guy is just left with a c, and then I'm left with x to the negative first power plus x to the negative second power. So all these other guys are essentially 1 divided by some form of x, which we know the limit equals 0 in those cases, divided by, if I factor x to the b out, I essentially have the same thing, d plus x to the negative 1 plus x to the negative 2. Of course, there could be coefficients in front of these guys, but like I said, if the limit approaches 0 in these cases, it doesn't really matter. Okay, so with this little trick in mind, I could come up with a set of rules that describe horizontal asymptotes. So I'm gonna call the following rules. So 3 situations can happen. The first situation is if a, this exponent in front of the numerator of x, is greater than b. So if that's the case, and I wanted to find this limit at infinity, well, if this exponent is greater than this exponent, there are more x's on top and at the bottom. So if I factor this out, I can get rid of all of this. Okay, this mess doesn't matter. The limit would be 0, and I'd have all that go away. I have x to the a over x to the b, and I can cancel out every x to the b. For every x to the a, there is some x to the b, and I'd have more x's on top. Okay, and even if I had the limit as x approaches infinity of 1 extra x on top, that would still be infinity. Right? So case number 2 would be if a is less than b, right? In which case, there are more b's than a's. So I would essentially come to a point where I'd have 1 on the numerator, and I'd have some form of x to some power on the bottom. So if I had 1 over x and I took that limit, we already saw that it would equal 0. So imagine if I had 1 divided by x to the third power, that would still be 0. You would just get there at a faster rate. All right, in the third case, the most interesting case, is if a equaled b. What would this limit at infinity equal? Well, if a equals b, these are the same quantity and I can cancel them out, and I'm just left with taking the limit of this junk. Well, as x approaches infinity, look at what happens to every single term with an x. This is 1 divided by x, this is 1 over x squared, 1 over x cubed, etc. And all of these guys would be 0, and I'd be left with c divided by d. So what this case tells us is if I have a function with the same exponent, like 5x to the 4th over 10x to the 4th, if these exponents are the same, then you look at the 5 and the 10, and that's your limit. Because these guys would go to 0, like I said, and they would essentially come to a point where they're growing at the same rate depending on what these coefficients are. So you just take the coefficients and divide them, and that would be your limit if these exponents were the same. All right? So if we were to do an example, so let's say I have the following function. Say I have m of x equals the following. And I want us to find the limit as x approaches negative infinity of m of x. Let's take a few seconds, look at that, and we'll come back and discuss it. All right, so a lot of you are probably saying to yourself, Alex, you misspelled sine and cosine, and I did not. Okay, so these are functions that are not seen a lot of times in school. This h symbolizes that it's a hyperbolic sine function and a hyperbolic cosine function. So the definition of these guys, it's actually pretty useful in engineering applications, but I'll just go ahead and define them for you. So hyperbolic cosine, or as I like to call it, I call it cosh, is the average of e to the x and e to the negative x. So I'm going to add these guys and divide by 2. Now hyperbolic sine or sinh as I call it, is essentially the opposite. So I take e to the x minus e to the negative x divided by 2. These are actually pretty cool. You can do an entire lesson on them. You can learn about the properties. You can learn that sinh squared minus cosh squared equals 1 instead of sine of x or sine squared of x plus cosine squared of x equals 1. It's actually a minus sign with hyperbolic functions. It's really cool stuff, but for the purposes of this problem, we can say the following. So given these definitions, I know that my function m of x is equal to, well, sinh, which we stated as e to the x minus e to the negative x over 2, minus cosh, which is e to the x plus e to the negative x divided by 2. Well, if you take a look at this negative sign, it would distribute to both terms, and what that would allow me to do is cancel out the e to the negative x, or e to the x, sorry. So I have e to the x minus e to the x. These terms would go away. And I have negative e to the negative x, negative e to the negative x. And I could combine those, and I have a negative 2e to the negative x divided by 2. Okay, so I'm just simplifying at this point. If you want me to show that extra step, I guess I could. So this would be e to the x minus e to the negative x. This negative would distribute. I'd have negative e to the x, negative e to the negative x divided by 2. And I'd have that guy and that guy cancel out. And these would combine to get me my negative 2. Since I have a negative 2 divided by 2, it can cancel that, and I'm left with negative e to the negative x. So that's m of x. I haven't done any calculus, I haven't done any limit applications. I've just stated that this function, after simplification, these definitions that I told you a few minutes ago, can be simplified to negative e to the negative x. Okay, so now if I'm actually taking the limit of this guy, as x approaches negative infinity, of negative e to the negative x, what do I get? Well, if you take a look at this guy, I'm going to factor this negative outside of the limit because, as I'm going to show you in a few more minutes, properties of limits, if I have some sort of a constant, which in this case would be negative 1, I can pull that outside and I'd get k times whatever this limit equals. So I'm going to say this is equal to negative whatever this limit equals. Okay, well, what is e to the negative x except just 1 over e to the positive x? But if I'm approaching a negative infinity, that's going to kind of reverse what I'm doing, right? So if I have e to the negative x, even if you want to graph this guy, so we're going to graph this guy, I have 1. So as x approaches negative infinity of this function, it would approach one way, but it would approach the other way if I'm taking e to the negative x. So as x approaches negative infinity, if you look at e to the negative x, it's approaching positive infinity. Okay, so this is negative positive infinity, which is just negative infinity. All right, so let me go over that again. The limit as x approaches negative infinity of a negative e to the negative x. The first thing I did was I said, all right, look, according to my properties of limits, I'm going to take this negative sign, I'm just going to pull it out front. So I don't have to worry about that right now. And then I'm just dealing with the limit as x approaches negative infinity of this guy. Well, try direct substitution, and I don't like it like this. I don't like doing this, but if you want to plug in negative infinity, like I said, it's not a number, it's a concept, but just for the sake of this, e to the negative and then whatever my x value is. Well, if it's negative infinity, if I plug that in, these negatives are going to cancel out and I'm going to be left with e to the infinity. Well, if I have an infinite power, if I'm raising e, which is like 2.71828, okay, if I raise that to the power of infinity, an incredibly large number, I'm going to get an incredibly large number. So this is going to simplify to positive infinity. But because we factor that negative sign out, you have to keep in mind that this is a negative infinity. Okay, so that's my explanation of that question. Okay. All right, so there are two concepts that I want to describe before ending this little section on limits. And the first one is called the Squeeze Theorem. Right? All right, so there are just two more concepts dealing with limits that I want to go over before we finish and move on to derivatives. And the first one is something called the Squeeze Theorem. And it states the following. So if I start with a picture, let's imagine that I have two functions. Okay, doesn't really matter what they look like, but one has to always be at least on top of the other one. So I have h of x, and then maybe I have some sort of an f of x that meets it at this point right here and does its own thing. So maybe call this guy h of x, and call this guy f of x. And there's a function that is always at least in between these guys. We'll call it g of x. Okay, so g of x can do whatever it wants, but then it meets at this point, and it continues to do its own little behavior. Okay, so just to state this for the record, it only has to be between these two functions for a range of values around x equals c. So the behavior has to be kind of similar around the point that you're studying. Okay, so in this case, we'll call x equals c. So the Squeeze Theorem says the following. If f of x is always less than or equal to g of x, which is always less than or equal to h of x, or in other words, if I have this double inequality that's either always decreasing, or in this case, always increasing. Okay, g of x is bigger than f of x, h of x is always bigger than g of x. Or it could be equal to it, like in this case, at x equals c. Okay, if I'm given a limit, or two limits to be exact, if I know that the limit as x approaches c of f of x is equal to the limit as x approaches c of h of x, if I know these two limits are equal, and if I know that it equals L, whatever L is equal to, so they're equal to the same limit, the same y value, they're approaching the same value on the function, then if you look at g of x, this limit also exists as x approaches c, and furthermore, the limit as x approaches c of g of x is also equal to L. So it's called the squeeze or the sandwich theorem because this function is essentially between, it's getting pushed in, shoved in these two functions, and as I'm approaching a value of c, if these limits equal something, this limit also has to equal the something. If these are so close, if they're getting so close to the same value, that means that this guy has to be squeezed in so that the limit is also the same thing. All right, so really quickly, why is the squeeze theorem relevant, and why do a lot of teachers neglect to include it in their lesson plans? Because it's not really that applicable. Well, imagine that I have another situation where I have two functions, and I know that one of the functions is always on top of another function. Okay, so suppose f and g are positive functions. You're always above the x-axis. And I know that the limit at infinity, so as x approaches infinity of f of x, eventually goes to some value L. Okay, let me just draw that. So I have a function that does whatever, it's above the x-axis, but it does whatever, and it eventually converges to this value of L. Okay. It's a horrible horizontal asymptote, but let's just say that converges to L. It eventually, the end behavior equals some sort of a value. Well, if I know that, and let's call this f of x, if I have a second function g of x, and I know that it is also a positive function, then I can tell you right now that it has to converge to a single value. That it can't just go off to positive or negative infinity. Okay, right? Because if this guy converges, then a function g of x also kind of has to converge to a value. It can't jump up too much. The reason this matters is for something called a series, right? So if I have a series that goes on and I keep adding these terms and it converges to a value, then another function that's in between two values has to also be convergent to a point. Now I don't know what that convergence is, I don't know what the value equals, but a big part of Calc 2 at least is determining whether a series is convergent or not. So the squeeze theorem goes a long way towards that. So just to state this for the record, so if g of x is less than or equal to f of x, so we can conclude that that limit also exists. Might not necessarily equal L, but it does exist. So this is equivalent, or this is relevant because of the convergence of a series. All right. All right, now before, or the very last thing that I stated in my first lecture is I talked about these two special limits, right? The limit as x approaches 0 of sine of x over x is 1. Limit as x approaches 0 of 1 minus cosine of x over x is 0. And I taught you a really dumb way to memorize it. And I told you that I would prove these, and we can actually use the squeeze theorem to prove both of these. I'm going to prove the harder of the two. Since there aren't a lot of geometric proofs surrounding this guy, I'm going to give that a shot. But it is going to take a while. So if you're not a proof person, or if you actually just don't care, you can just skip this part of the lecture. All right. Really wish you wouldn't, but you can do whatever you want. So I claim that the limit as x approaches 0 of 1 minus cosine of x over x equals 0. So take a deep breath. This is going to be a long one. All right, so let's suppose that I have a picture, and I'm going to draw a unit circle. So that's essentially a circle with radius 1. Okay, that's really not the best circle, but you can get over it. This distance is 1. And I have the following. I have 2 points on this circle that I'm concerned with. The first point is going to be the point that's directly to the right of this unit circle, still in the circumference, and that is essentially, well, it's 1, 0. And then I have an arbitrary point that can be anywhere. I'm going to make it in the first quadrant. You're going to see why eventually. But what is that point equal to? Well, in trigonometry, near the middle of trigonometry, you should have learned that any point on the unit circle has the coordinates cosine of theta, comma sine of theta. Right? So I'm going to form a triangle between the origin, this arbitrary point on the circumference, and this point directly to the right of my center of my circle. Right? Okay, so this has some sort of an angle theta. Okay, and I'm also going to do something that's going to allow me to do some right angle trigonometry. So I'm going to drop this guy down. So I have a height component. And I also have right angles. Okay, so what is this? So this guy is at a point cosine of theta, comma sine of theta, which means that this distance right here is cosine of theta. And this distance here, which I'll do in a different color, so that's sine of theta. Right? And furthermore, because I know that this is a unit circle and this entire length is 1, if this is cosine of theta, I know that this length right here, has to be 1 minus cosine of theta. Right? Because if you take 1 minus cosine of theta plus cosine of theta, I get the entire radius of the circle, which is 1. Why is that relevant? Well, in my proof, I wanted to prove 1 minus cosine of x over x. And I should be consistent with my variables. I apologize for that. We'll make this guy theta, as theta approaches 0. My apologies. But if you add these guys together, you get 1. But this is going to allow me to take 1 minus cosine of theta, and that's a part of what I'm trying to prove. So that's why I did that. Okay, so I'm going to redraw this triangle. I'm going to enlarge it a little bit. Okay, so I'm going to drop this guy down. I have right angles right here. And I want to point something out. I want to point out that, well, since this guy is starting from the center and it's going on the circumference of the circle, that has to have a length of 1, right? The radius all along this unit circle is 1, so it doesn't matter if I'm right here or here, these two distances have to be 1. But the point of the matter is they're the same. So this side is equivalent to this side, ergo it's technically an isosceles triangle, and I know that these angles, by the definition of an isosceles triangle, I know a theorem that states that if these lengths are the same, that angle and that angle are congruent, which is going to be important later. So technically they're both 1, but regardless they're identical, and therefore these two angles are identical. Alright, so if I were to set up this triangle a little better, okay, what I can say is this angle is theta. Right? That angle is theta, and since this is a right angle, I know that this angle is 90 minus theta. Alright? Furthermore, I have to call this hypotenuse something. I'm just going to call it h. It really doesn't matter what it's labeled, but we're going to call it h. The one thing that I don't know is what this angle equals. So that's arbitrary as well. I'm just going to call it y, because why not? I'm going to call that angle y, and therefore this guy, since this is a right triangle as well, I'm going to call this guy 90 minus y. So if I wanted to come up with some sort of a relationship between theta and y, why would I want to do that? Because I know that 1 minus cosine of theta is in my proof. I really want that. But the only right triangle trigonometry I can do with this side, which I said was 1 minus cosine of theta, is with this arbitrary angle y. So I need some sort of a relationship between y and theta so I can connect the dots. I'm going to serve that as an intermediate so I can talk about 1 minus cosine of theta. Well, like I said before, this is an isosceles triangle. Can't emphasize that enough. So this angle right here, this entire angle, is equivalent to this angle right here. So I can say that 90 minus theta plus y, right? These two angles combined equals 90 minus y. And if I can say that, well, I can do some algebra manipulation, cancel these 90s out, and I can say eventually that 2y is equal to theta, and therefore y is equal to theta over 2. So I'm circling it because that's extremely important that we know as far as how our proof is going to go. All right. So what can we do with this? Well, I know what sine of y equals from trigonometry. I know that if this angle is y, sine of y is opposite over hypotenuse. It's opposite, which is this 1 minus cosine of theta, divided by the hypotenuse, which is h. Now that's not what I wanted in my proof technically. I wanted to prove 1 minus cosine of theta divided by theta. I don't have theta, I have h. But here's what I know about circles, right? If I have a circle, some sort of an angle theta, I know that this arc length can be found using the formula arc length S equals r times theta. Well, that's fantastic. Why is it fantastic? Because I know that this is the unit circle. I made it the unit circle so that the radius would be 1. So therefore, my arc length equals 1 times theta, or just theta. So if I have an angle theta, this arc length is also theta. So I'm starting to connect the dots between h and theta, and I'm realizing that, well, if this is h, these are 2 points connected to the line segment. That is the shortest distance between any 2 points, is a line segment. Therefore, any other path, like this distance right here, is always going to be greater than or equal to this line segment. So if this line segment is denoted h, then I know that theta, this arc length right here, is greater than or equal to h. And since I know that, 1 divided by theta is less than or equal to 1 over h. Whenever you flip two sides of an inequality, you always have to flip the sign, right? If I had something like 1 is less than 5, and I flip these guys to be 1 and 1/5, well, you'd obviously have to flip the sign so that 1 is greater than 1/5. Okay, so if I flip these guys, I have to flip the inequality symbol, and I know that 1 over theta is less than or equal to 1 over h. So now what I'm going to do with this, just to state this for the record, 1 over theta less than or equal to 1 over h, I'm going to multiply both sides. I'm going to multiply both sides by 1 minus cosine of theta. So multiply this side by 1 minus cosine theta. Multiply this side by 1 minus cosine theta. And I get the relationship I've been looking for. 1 minus cosine of theta divided by theta is less than or equal to 1 minus cosine of theta over h. Right? Now, 1 minus cosine of theta over h, well, we kind of described what that was equal to, right? This guy connected over here was equal to sine of y. Furthermore, we also connected y to be equal to theta over 2. So by all these transitivity statements that I'm making right here, I can say that if this is true, then 1 minus cosine of theta over theta, what I'm trying to prove is less than or equal to sine of y, right? Because this relationship right here, this 1 minus cosine of theta over h, I'm trekking it back to the definition of sine of y, opposite over hypotenuse. Furthermore, given that this is an isosceles triangle and that these guys are equal, theta is equal to 2y, or y is equal to theta over 2. So instead of sine of y, I'm going to say this is equal to sine of y, which is equal to theta over 2. It's very important that I make that statement, right? Now I'm going to rewrite this. I guess you don't have to. I did my notes, but I don't have to. So 1 minus cosine of theta over theta. Let's talk about this for just a second. So what are some restrictions on what this can be equal to, or what it can be between? Well, cosine of theta, by definition on the unit circle, can at most be positive 1, and at least, like, the minimum value is negative 1. So if I look over here, cosine of theta, worst case scenario, it's negative 1. So I have a 1 minus a negative 1. So maybe I should write this down. So cosine of theta is between 1 and negative 1. So 1 minus cosine of theta has a minimum value of 1 minus, well, it wouldn't be negative 1 because that would bring it to a 2. So the minimum value would be 1 minus 1 divided by theta, which is 0. The maximum value for this guy would be 1 minus a negative 1 divided by theta, which is a 2. Furthermore, cosine of theta is only 1 whenever theta is 0. Okay? Or pi, but we're staying in the first quadrant. So it can never actually be equal to 1. Right? Because if cosine of theta equaled 1, theta was 0, and we'd be dividing by 0. But I'm going to kind of ignore that for now and state that my restriction is that this guy has to be positive, has to be greater than or equal to 0. It can never be negative, right? Because the maximum value is 2, the minimum value is 0, right? 0 divided by whatever theta is. So I'm going to say furthermore that this guy is greater than or equal to 0. Okay, so I really need you to understand that this double inequality is crucial for proving this guy. So just to do a 20-second recap. All right, so what I want to prove is that 1 minus cosine of theta divided by theta, the limit as theta approaches 0 is 0. In order to get this guy, I had to manipulate a right triangle and use a relationship that y, sine of y, equals 1 minus cosine of theta over h. Well, I know that 1 minus cosine of theta over h has to be greater than 1 minus cosine of theta over theta because theta is greater than h. Because that's the shortest distance connecting those 2 points, which we define to be h. Theta has to be greater than that. So if I flip them, I have 1 over theta. 1 over theta is less than 1 over h. So with that relationship, I multiplied both sides by 1 minus cosine of theta, and I got the relationship that I wanted to. Furthermore, I know that this 1 minus cosine of theta over theta has to be greater than or equal to 0 because cosine of theta can only oscillate between -1 and 1. And both of those would meet this criteria. Okay, so now with this, I stated the squeeze theorem. You'll recall what the squeeze theorem is. It states that if I have 3 functions related by a double inequality, such that one is less than or equal to another, which is less than or equal to a third, and I knew that the limit as x approaches c of both of those equal to value, the limit of this guy exists and it's equal to the same thing. So let's do that. So I'm going to go over here and I'm going to take the limit as theta approaches 0, of the left, okay? And I claim that that is equal to, it's equal to the same thing as the limit as theta approaches 0 of the right sine of theta over 2. Well, sine of theta over 2 is a continuous function, which means I can plug this limit in and I can get sine of 0 over 2, which is 0. Okay, and the limit of theta as theta approaches 0 of 0, 0 is a constant function. Regardless of what I'm approaching, the function is going to be 0. Both of these equal 0. And by the squeeze theorem, by the stipulation that I laid out to you just a few minutes before, if these equal each other, if both of these limits equal 0, and that's squeezed in between, that limit exists, and therefore the limit as theta approaches 0 of 1 minus cosine of theta over theta equals 0. I proved that using the squeeze theorem in a lot of geometry. All right? So that's the squeeze theorem. And you can prove the other one. Normally people prove, where did I put it? Normally people can prove this one. They prove this one using geometry, and they prove this one by using this one. But it would be a nice exercise to go backwards and use this guy to prove this guy analytically. Need my help with that? Just state it in the comments. All right. So the last little bit that I want to go through is talking about the limit idea in a more formal manner. So last lecture, I drew up a diagram like this. And I talked about the informal definition of a limit. And I stated that if the limit as x approaches c, the limit as x approaches c of a function is just equal to a value L. Because if I invent a range of values around c, call it x sub L and x sub R, if these guys approach c, what's going to happen to the actual function is they're going to converge on some f of c. And I can only say f of c if it's defined, but even if it isn't defined, it's going to converge on some value L. So that's informal. So what I'm going to ask is, why is this informal? Well, what do I actually mean when I say as x approaches c? Because if you look at it right here, look right here. As my x sub L and x sub R move closer to c, my function value has different gaps. Let's say these have consistent gaps, but the function changes. So this gap just happens to be wider than this gap. So I really have to be specific when I say as x approaches c. So what do I mean by that? Well, just like in this little example, I mean there's some sort of a range of x values around c, and there's a range of y values around my limit. Okay, so what I mean by that, some range of x values around c, And as a result, because of this range of x values, we've seen plugging the endpoints of that range in, there's a range of y values. Or in the limit, which we're going to call f of c, but I could just as easily call it L. Okay, so what else do I mean? What would happen if I converge in on C, if I decrease this range? Well, you should say that the range in the y values would also decrease. So as this x range decreases or increases, the y range does the exact same thing. By the way, please don't confuse the word range with domain in range. I'm talking about range definition-wise as just a group of x values or y values, a group of points that surround a given value. Okay? So because of this, I can say that the y range is proportional to the x range. All right, if my x range decreases, so does my y range. If it increases, the y range does the same thing. So because they're proportional, that means that there is some expression that relates these guys for every function. That's going to be different depending on the function. Okay, like this guy, like I said, this range between f of c and the right endpoint is greater than f of c and the left endpoint, and that's because the function is increasing. So if it's increasing, obviously the further I go out to the right, the more my function is going to increase by, and this is going to be greater than this guy. All right. All right. So if my y range is proportional to my x range, then I'm just going to make a statement that the y range, which we're going to define very formally in a minute, the y range is equal to some constant. I don't know what that constant is. We'll call it k. Some constant k times my x range. But if you can find this expression, then you have essentially proved that this limit exists. You've proved that I can make the y range as small as possible, and I can find an x range that will make the y range as small as I want to. For example, I can make the y range 0.01 of whatever my limit value is. So whatever my limit value is, plus or minus 0.01, well, if I can find an expression relating y range and x range, I know that I can come up with an x range that'll give me a y range. That's essentially the definition of a limit, right? So suppose this x range is represented in the following way. It's represented by x minus c, the absolute value of x minus c. So if you want to review your properties of absolute value, what that essentially says is, I'm talking about the distance between an x value and my c. That's what this says in English. The absolute value of x minus c states that wherever my x is, I'm subtracting it from some central c that doesn't change, but I'm changing my x. I'm looking at the distance between that. And it's always positive because it's an absolute value, and distance is always positive anyway, so that matches. It could be on this side or this side, and the absolute value of x minus c would be the exact same. Furthermore, as this limit decreases, or as the limit that we're studying decreases, it's going to decrease this distance. Then I can say that this distance is within some number, we'll call it delta. Okay, so back to my picture. Wherever my x is, we're going to say it's within a range. We're going to call this distance delta. So I have a negative delta and I have a positive delta, and my x has to be within that. Right? Again, please review your properties of absolute value if this doesn't make sense. Right? So likewise, because I said there's a relationship between the x values and the y values, I can say that if there's a range of x values, the distance between my function and my limit value also has a y range. So what this means, tracking it back to my good old picture, is if I have some sort of a range, we'll call it delta. So negative delta, positive delta, it's a distance of delta that my x has to stay within. The distance between x and c can at most be delta. Then my function value has to also be within a range that is at most epsilon, right? Wherever my function f of x is equal to, that has to be, the distance between that and my limit has to be within some epsilon. So therefore, I'm going to make the following formal definition of a limit. So I'm going to start out the same way. The limit as x approaches c of this function is still equal to L if the following. If the distance between my function value and the limit is within epsilon, whenever the distance between my x value and c is within delta. Okay, so what that says in pure English is this. If I can find a range of y values, and we'll call it epsilon, and I can find a range of x values, and we'll call that delta, and if there is some expression that relates delta and epsilon, then I have proved that this limit equals L. Because I have proved that for every single range of y values, there is a range of x values that matches that. So if I make my range incredibly small, which is the idea of a limit, I make it essentially 0, but it never equals 0, but if I make it essentially 0, there's some delta, there's some range of x values that will also match that. So if you can prove that there's an expression relating delta and epsilon, you've essentially proved that the limit exists. Okay, so we're going to do two examples. I'm going to try to make them as quick as possible, but I do want you to see them.